Okay, so welcome to another video. Today we're doing another GCSE paper. This time it's a 2018 series. I'm going to kick things off with paper 1. So the first question then, we've got some socks, and we're told that a student becomes negatively charged because of the friction between the socks and the carpet, and essentially when they start walking on this carpet. And so why does that friction actually cause the student to become charged? Well, the key here is that we have a transfer of electrons. When something becomes charged, it's due to a transfer of electrons. Those are responsible for electrical charge. And which direction is are the electrons going to be transferred then? Well, the student becomes negatively charged, which tells us that the electrons are transferred from the carpet to the student. And that's all you should need for the first 2 marks of this paper. Okay. The next question then, the student's head is presented by the sphere in figure 2. The student is negatively charged and the arrow shows the electric field or part of the electric field around it. And we're asked basically, can we complete this electric field? And so with an electric field, it shows a direction that a positive charge would be moved towards. So essentially we see this arrow that's indicating the positive. If we put a positive charge in this field here, it would move in this direction. So we just want to complete it for the rest of the field. And the key thing here is that the arrow is always going to be pointed towards the negatively charged sphere. And also the field lines, we're going to draw them perpendicular to the surface of this sphere. And they should kind of be evenly distributed around the sphere as well. The next question, the negatively charged student touches a metal tap and receives an electric shock. Explain why. Well, first of all, the student is negatively charged. The metal tap we assume is going to be electrically neutral. And so there's a potential difference between the student and the tap. And that actually is what causes, once again, we have a transfer of electrons. And so when you have a potential difference, you make an electrical contact, then you end up with a transfer of electrons. And once again, we want to say the direction that the electrons are actually transferred from or to. And so this time it is from the student to the tap. And what we need to say for the final mark here of the 3 marks is that essentially this causes the tap, this causes the charge to be earthed. And what that means is that essentially the excess negative electrons from the student flows into the tap, where there's all sorts of electrons, and essentially it flows away and is dissipated through that tap. Okay, 1.4, some carpets have thin copper wires running through them. The student is less likely to receive an electric shock after walking on this type of carpet. Explain why. Well, essentially the first thing we need to understand is we've got copper, and copper is essentially a conductor. So copper is a good electrical conductor. And why does that actually mean that we don't get an electric shock? That means that essentially we don't get this build-up of charge, okay? And that should be enough for your 2 marks. Essentially, you have no build-up of charge. If you have no build-up of charge, then you end up basically having, you can't maintain a potential difference between the student and the carpet or whatever, the student and the object, and so you get no electric shock. A teacher used a Geiger-Müller tube and a counter to measure the number of counts in 60 seconds for a radioactive rock. We've got a count 819 counts in 60 seconds, and we've got background radiation of 0.3 counts per second. So first of all, we want to calculate the count rate. Well, we just do 819, and remember rate, that is basically per second. So you divide by the number of seconds, which was 60. So 819 over 60, and if you put that into your calculator, should get a count rate of 13.65. But they've also given us this 0.30 counts per second. This is basically the background radiation count rate. So whenever we have background radiation, we want to correct for it when we take our measurement. So actually it's 13.65 minus the background radiation. This gives us the actual radiation that is being produced from the rock. So that should give us 13.35. 2.2 is householder is worried about radiation emitted by the granite worktop in his kitchen. We know that 1 kilo of granite has an activity of 1250 becquerels, and the worktop has a mass of 180 kilos. Therefore, what's the activity of the whole worktop? Well, we know that per kilo is 1250, and we've got 180 kilos of it. So we just multiply those two together. And when you do that, you should get 225,000 becquerels. 2.3, the average total radiation dose per year in the UK is 2 millisieverts. Table 1 shows the effects of radiation dose on the human body. The average radiation dose from the granite worktop is 0.003 millisieverts per day. Explain why the householder should not be concerned about his yearly radiation dose from the granite worktop. Well, we can see actually that the lowest dose that actually causes cancer is 100 millisieverts. And if we have 0.03 millisieverts per day, then we can actually work out what is the yearly dose, right? So 0.003 multiplied by the 365 days, if he's exposed every single day of the year, what would his dose be from the worktop? It works out to be 1.095 millisieverts. Okay, and the idea is that this is much lower than 100, and 100 is the lowest dose that actually causes cancer, so he actually has nothing to worry about. Bananas are a source of background radiation. Some people think that the unit of radiation dose should be changed from sieverts to banana equivalent dose. It's just one reason why the banana equivalent dose may help the public to be more aware of the radiation risks. So this is a suggest question, so any kind of sensible reason that you can think of should be able to get you the mark. And the idea is that why do we want to actually use something called a banana equivalent dose? Well, people know what a banana is, so we can kind of compare the risk. People know essentially that if something is worth 2 banana equivalent doses, then that would be equivalent to them eating 2 bananas. Instead, if you give this sievert, it's a bit abstract, people aren't really too sure. So that's one reason why you might want to change it to a unit like that. Question 3 then, a student investigated how the resistance of a piece of nichrome wire varies with the length. So we've got a diagram of the circuit that they used there, and they basically want to complete the figure 3 by adding an ammeter and voltmeter. So we can see the wire that is measuring is over here, and essentially want to work out the resistance of the wire from our circuit. So we need the both the current and the voltage, and so we need to know how to measure these. Okay, we use an ammeter and voltmeter, and how do we actually set them up? Well, let's do the voltmeter first of all. So the voltmeter, you connect in parallel, and we want to connect it in parallel to the thing that we want to measure the potential difference of. In this case, we want to measure the potential difference of the wire, so we connect it in parallel to the wire. The ammeter, on the other hand, well, this is a series circuit, so the current at any point in the circuit is going to be the same. So we can put an ammeter in here like this, and the current at this point would be the same as the current basically flowing through this whole circuit, including through this wire. So you can put the ammeter where you want, basically. And that's it. Cool. Question 3.2 then. This time we got a 6 marker, and the question is, describe how the student actually obtained the data for the investigation. So this is a 6 marker question, and the question is essentially asking us to go step by step through this experiment and what we do. And because it's a 6 mark experiment question, we really need to give a lot of detail and describe every single step. So I won't write this down, but just to talk you guys through it. Essentially, some things that you might want to do first of all is actually measure the length. And so remember, we're looking at how does the resistance vary with the length. Well, the first thing then that we need to do is actually measure the length in the first place. Now we want to give lots of detail. How do you measure the length? So you can say you could use a ruler, you could use calipers, something like that. Then you want to vary the length. How are you going to vary the length? Well, you're going to measure it to different lengths and then cut the wire at those appropriate lengths. Next step, you want to actually measure the current. How do you measure the current? You read the reading off of the ammeter. You also want to measure the potential difference. How do you do that? You read the reading off of the voltmeter. Now, are you done there? Well, you also want to take repeat readings. So maybe you switch the circuit off, you switch it back on again, and you measure take your readings again for the current and your voltage. Then you can measure so you can work out the resistance from that. So you might want to give the formula V equals IR, and if you rearrange that, R equals V over I. So you do the potential difference that you took off your voltmeter and your current that you took off your ammeter, and you can work out your resistance. And remember, you've taken repeat readings, so you can work out the average resistance for the wire at that length. You then vary the length of the wire, switch it out, and you start again. When you have that, what you can do is actually plot a graph of the resistance against length. Okay, so remember, we're looking how does the resistance vary with the length. So a good way to actually see that would be to plot it on a graph. And then you can kind of understand that that's how you would do your investigation. Now in the question we've also asked, we should include a risk assessment for one hazard in the investigation. So there's a few different hazards you could use, but one of them could potentially be if you use a high current, what could actually happen is the wire would overheat or melt. And you might have seen this before when you do experiments in the classroom. Put a particularly high current through quite a thin wire. This could actually cause it to smoke or melt. It could be quite dangerous. If you touch it, you could get burnt. So what's a precaution that we can take to prevent that risk is to actually use a lower current to ensure that we don't get this wire overheating. Okay, and that should be enough detail for 6 marks. Okay, 3.3 then. Why would switching off the circuit between readings have improved the accuracy of the student's investigation? So it's multiple choice. Either the charge flow through the wire would not change, the potential difference of the battery would not increase, the power output of the battery would not increase, or the temperature of the wire would not change. And we kind of alluded to it in the question previously, but essentially when you have the current flowing through the wire, it does cause the wire to heat up. So if you want to actually switch off the circuit between readings, will ensure that the wire is allowed to cool down between the readings. And one thing that does happen when you increase the temperature, the conductor could essentially start to behave in a non-ohmic way. And you guys might know a little bit about that. You should know what the difference between an ohmic and a non-ohmic conductor is. But essentially the temperature of the wire itself could affect the resistance. Okay, 3.4, the student uses crocodile clips to make connections to the wire. They could have used a piece of equipment called a jockey. So here there's a crocodile clip and here is a jockey. And how would using the jockey have affected the accuracy and resolution of the student's results compared to using the crocodile clip? So essentially, if you use a jockey, would the accuracy be higher? Would the accuracy be lower? Would it be the same, or would the resolution of the length measurement be higher, or would the resolution of the length measurement be lower, or would the resolution of the length measurement be the same? So here we want to tick 2 of these boxes. So first of all, we can see essentially how a jockey works. So the idea is that the crocodile clip clips directly onto the wire, but you can see the area of effect of the crocodile clip is sort of quite wide, and if you can read that off of the ruler, you could get some kind of reading. Maybe we could estimate it be about 5 millimeters. In comparison, then, if we take the jockey, we take the tip where it makes contact is much thinner. You can see it's probably 2 or 3 millimeters in comparison, so it's much thinner base. So how does that actually affect first of all the accuracy, right? So it's 2 marks, so it's going to be one of these and it's going to be one of these. And so for the accuracy, will the accuracy be, will it actually be higher because we're able to more accurately measure the length of the wire. So that means that when we do our results, there's going to be less error in the length because this tip here is much more narrow, so you can get more accurate reading. What will happen to the resolution of the length measurement? And the resolution of the length measurement would also be higher. And again, why would it be higher? Well, the idea is that if we zoom in over here, because this is so thick, our crocodile clip contact, the length measurement that we could take would be anywhere from this edge here, so doing a different color, anywhere from this first edge to the second edge, and that would, we could technically take the measurement or the reading for the length anywhere from there to there. Same thing for the jockey, but this time the length measurement would be much more narrow, and so the resolution is actually going to be a lot higher as well. So hopefully that makes sense. Question 4 then shows a cyclist riding along a straight level road at constant speed. Complete the sentences. As a cyclist cycles along the road, the something energy stored in the cyclist's body decreases. Well, whenever we have a human exerting some kind of effort with their muscles, that tends to be a chemical energy store. And the speed of the cyclist is constant when the work done by the cyclist is what compared to the work done against air resistance? Well, it would actually be equal to. Right, so when we are when the energy transferred is equal to the energy needed to overcome air resistance, that means our speed is staying the same. Figure 6 shows how the speed changes as the power output of the cyclist changes. Write down the equation that links power, time, and work done. So we should know that the power is equal to the work done divided by the time. Calculate the work done by the cyclist when his output power is 200 watts for 1800 seconds. So we could just plug this into our equation. And so the power is 200 watts. And that is equal to the work done divided by the time, which was 1800 seconds. And so 200 multiplied by 1800 seconds gives us the work done, which is equal to 360,000, and the units is joules. Point 4 then, calculate the percentage increase in the speed of the cyclist when the power output changes from 200 watts to 300 watts. So when the power is 200 watts, what was the speed of the cyclist? We're going to use the graph. So you go to 200 watts, use a ruler, go up to the point and come across to the y-axis, and we can see the speed was about 9. Then we do the same at 300 watts, we go up to our curve, and then we come across, and we can see the speed here is about 11. So the difference in speed is approximately 2. So from 9 meters per second to 11 meters per second, and again these readings depend on how you read your graph. So actually we can actually be a little bit more accurate. If we come across here, you can see that this is not 9, this should be actually be 9.5. So each graduation is worth 1, so that's 6, that's 7, and so on. So this is actually 9.5. So the difference in speed is 1.5 meters per second. And so what is the percentage increase? So we want to use the base speed, which is not 9 but 9.5. So the increase was 1.5. What's that as a percentage of our initial speed? 9.5. So 1.5 divided by 9.5, and we want it as a percentage, so times by 100%, and that should give you 15.8%. Okay, so hopefully that makes sense. 4.5, the maximum speed this cyclist can travel on a level road is 14 meters per second. How does cycling uphill affect the maximum speed of the cyclist? Well, first of all, the maximum speed is lower. Well, and you should kind of instinctively know that obviously going uphill is going to be much more difficult than going level or downhill. But it's 3 marks, so we need to give 3 different points here. So the maximum speed is lower, that's enough for 1 mark. But why is the maximum speed lower? Well, the maximum power output is going to be the same, right? The maximum power output is constant. The cyclist can't increase his maximum power output, but the actual work done against gravity is now a lot higher. So, but essentially we have an increased work done against gravity. Now, why does that mean that the cyclist is slower? Well, essentially, if you're doing more work against gravity, that means you've got less excess energy, which can be transferred to kinetic energy, and so that means your speed is going to be lower. 5.1 then, we want to complete the sentence, and so the current through an ohmic conductor is directly proportional to the watt across a component. Well, it's directly proportional to the potential difference. And the next part of the question then, provided that the watt remains constant. So this is only true if the temperature remains constant. So remember, with an ohmic conductor, usually you have a directly proportional relationship between the current and the potential difference. However, that can change if the temperature increases or decreases by a lot. 5.2 then, figure 7 shows a current potential difference graph for a filament lamp. Explain how the resistance of a filament lamp changes as the potential difference across it increases. So what we can see is that when the current increases, the temperature of the filament lamp also increases, and that causes the resistance to increase. So how do we tell the resistance from a current potential difference graph? Remember, V equals IR, which means that the resistance is equal to V over I. In other words, is essentially the inverse of the gradient gives us the resistance. And so what we can see is that as the gradient is changing, that means the resistance is changing. So what we can say is that the current increases. That when the potential difference increases, that causes the current to increase. If the current increases, you get a higher temperature. If you get a higher temperature, that causes the resistance to increase. And that is basically that for 3 marks. You'd say those 3 points and you'd write it out in a nice flowing sentence, and that should give you the 3 marks. 5.3 then, many householders are replacing their filament lamps with LED lamps, which are more energy efficient. So what does actually being energy efficient mean? And so we can kind of define it that essentially efficiency is equal to the useful power or the useful energy over the total energy. And so when something is more efficient, it means that essentially you have less wasted power. Less wasted power or energy. You can use those both interchangeably. Alternatively, you can say basically the reverse, that you have more useful energy or a higher proportion of useful energy from the total energy. So the next part of the question then, we have a light dependent resistor and it's used to turn on an outside lamp when it gets dark. And so part of the circuit is shown in figure 8. And basically we're told that the light intensity decreases. What happens to the potential difference across the LDR and the current in the LDR when the light intensity decreases? Well, we should know that for a light dependent resistor, the resistance is actually higher when the light intensity is lower. So therefore, if you have a higher resistance, that means the potential difference across the resistor is going to be larger. So the potential difference increases. So essentially more of this 12 volts is going to be across this resistor. And what happens to the current? Well, when you have a higher current, when you have a higher resistance and a higher potential difference, you then get a lower current. Okay, next part of the question, what is the resistance of the LDR when the potential difference across it is 4 volts? You want to give a reason for the answer. And so if the potential difference across the LDR is 4 volts, that means that the potential difference across this part of the circuit or this resistor would be the remaining part of the potential difference from this battery. And so that would be 8 volts. And so we can see therefore that with 2000 ohms there's a voltage of 8 volts. So with 4 volts you'd have basically half the resistance. So you expect the resistance to be 1000 ohms. And so the reason then, we say the resistance first of all is 1000 ohms. The reason for that is that the resistance or the potential difference in a series circuit is shared in proportion to the resistance. So you write that down, potential difference is shared in proportion to the resistance. Hopefully that makes sense. 5.6, calculate the current through the LDR when the resistance of the LDR is 5000 ohms. Give your answer to 2 significant figures. So this time we want to work out in a little bit more detail. And so let's scribble this out. So this time we're told that the resistance is 5000 ohms. So first of all, we can work out the total current in the circuit by using V equals IR on the whole circuit. So if you could write this out. And so the total current would be equal to the total voltage, which is 12. And that is equal to, well, divided by R, and the total resistance is going to be basically these two are in series, so we just add the individual resistances up. So 2000 plus 5000 gives us a total resistance of 7000 ohms, and so 12 over 7000 will give you the current, and you put that into your calculator, you should get 1.71 times 10 to the minus 3 amps. So this is the total current in the circuit. And now we want to work out the current through the actual resistor. Well, actually this is going to be the same thing because it's a series circuit, the current at any point in the circuit is going to be equal to the current at any other point. So the current through here is going to be equal to the current starting here or wherever. So we worked out then that the current is 1.713 times 10 to the minus 3 amps. And we want to give it two significant figures, so 1.713 times 10 to the minus 3 to two significant figures. That's your first significant figure, that's your second significant figure, so it's just 1.7 times 10 to the minus 3 amps. Question 6 then, smoke alarms contain an alpha radiation source and a radiation detector. Figure 9 shows part of the inside of a smoke alarm, and the smoke alarm stays off while alpha radiation reaches the detector. Why does the alarm switch on when smoke particles enter the plastic casing? And so the idea here is that the smoke, essentially you can see here what's going on. We've got an alpha radiation source, and it's basically releasing this alpha radiation and then hitting this radiation detector, and this is connected to the alarm circuit. So what happens when we have smoke coming in? We can see here the smoke basically absorbs the alpha ray radiation, and that causes the this detector to no longer detect the alpha radiation, and that is connected to the circuit, and that will cause the alarm basically to go off. And so the smoke absorbs the alpha radiation. Why is it safe to use a source of alpha radiation in a house? Well, we need to understand essentially what causes the danger in radiation, and a lot of that is to do with how penetrating it is. And alpha radiation is not very penetrating, and it doesn't actually penetrate human skin. So it does not penetrate human skin, and humans are basically what would be living in the house. The smoke alarm would not work with a radiation source that emits beta or gamma radiation. Explain why. Well, beta and gamma radiation are more penetrating than alpha radiation. So for beta or gamma is actually so penetrating that it will penetrate the smoke. The smoke will not be able to absorb it. And that means that you basically you don't interrupt this flow here, and so there would be no change in the count rate detected. So no change in detected count rate. Cool. 6.4 figure 10 shows how the count rate from the radiation source and the smoke alarm changes with time. So essentially we've got the time and half-lives on the x-axis and the count rate in counts per second on the y. Smoke alarm switches on when the count rate falls to 80 counts per second. Explain why the radiation source inside the smoke alarm should have a long half-life. Well, if you have a long half-life, that essentially means that your count rate will be stable for a long time. So you can see that as time goes on, the count rate will steadily decrease, and so by the time you get to sort of 1 point something half-lives, the count rate will decrease below 80. So if you can imagine, if you have once that happens, essentially the smoke detector is not very useful, and so what we want is that we want the smoke alarm to maintain a count rate above this, a normal count rate above this 80 level for as long as possible, as basically when it dips below that, that means that the smoke alarm is no longer useful. And so if you have a large half-life, it means you get a constant count rate, a more constant count rate, until about, so you get longer time until about 1.3 half-lives. So you can kind of come across and see this is approximately 1.3 half-lives until 1.3 half-lives, at which point, like we mentioned, it is no longer useful. So at that point it dips below the 80 counts per second. Right, 6.5 then. Figure 11 shows a patient who has been injected with a radioactive source for medical diagnosis. Explain the ideal properties of a radioactive source for use in medical diagnosis. And this is 4 marks. So you want to give an answer worth the 4 marks there. And so the idea is that some things that you can mention is that you have something with a short half-life. So why do you want something with a short half-life? Well, something with short half-life will cause basically less damage to cells, essentially. If you can imagine, if you have something with a short half-life, it means it's going to degenerate very quickly, and so it's going to be able to cause less damage because it's going to be in there for a lower amount of time. The next property we could mention is once have something which has a low ionizing power. So something which is not ionizing, and why do we actually want that property when we use something for medical diagnosis? Well, it's less likely to cause cancer, to damage cells or cause cancer, basically. That's actually the key thing. And that should be enough for the 4 marks. You kind of get 2 marks for each one, but a few other things you could say is you want something very penetrating. Why do you want it to be penetrating? Well, we want to actually detect it outside the body. And what kind of radiation would we generally want? Well, we kind of want gamma ray radiation over beta and alpha, since gamma ray radiation is the most penetrating but is also the least ionizing. And so that's a few points you could say. Question 7 then. A student investigated how the pressure exerted by a gas varied with volume of the gas. So we have a diagram of the equipment used there. So you've got a pump, a pressure gauge, and a gas in a tube. So we use the pump to compress the gas in the tube. As the volume of the gas decreases, the pressure of the gas increases, right? So you've got the same amount of gas particles inside the tube, but we use the pump basically to decrease or increase the volume. Student only recorded 1 set of results. Give 2 reasons why taking repeat readings could provide more accurate data. Well, we should know why do we actually use repeat readings. First thing is be able to calculate a mean. When we calculate a mean, it gives us a more accurate result. Or we can also use repeat readings to identify anomalies. So those are the 2 points I'd put there. If you take repeat readings, you can easily see if one of your readings is completely out of whack. The next point then, 7.2, figure 13 shows the position of the student's eye when taking volume measurements. Explain what type of error would be caused if the student's eye was not in line with the level of the liquid in the tube. So you can see here, student's eye is about in line, and that's what we'd want. If it's not in line, there's a few different names. You could call it parallax error, but more commonly, parallax error is to do with when you take measurements at an angle. But we can also just call this random error. So this is kind of more of an answer of what would be expected. So it's random error because if you take it at a different point each time, then you kind of read it slightly wrong each time. So you have some random error there. So that's what we'd say for the 2 marks is random error. And why is it random error? Because the eye is in a different position each time. 7.3, if the gas is compressed too quickly, the temperature of the gas increases. Explain how the temperature increase would affect the pressure exerted by the gas. And so if you have an increased temperature, what actually happens to the pressure is that the pressure also increases. So this would lead to an increase in the pressure. Why does that actually lead to an increase in the pressure? Because when we have a higher temperature, this causes a higher kinetic energy within the molecules of the gas. So the individual molecules have more kinetic energy. If they got more kinetic energy, essentially that means that they're able to bounce off the walls at a quicker rate, and that's basically what pressure is. So that should give you your 2 marks. 7.4 then, one of the students' results is given below. We've got the pressure 1.6 times 10 to the 5 pascals, and we've got the volume 9 centimeters cubed. Calculate the volume of the gas when the pressure was 1.8 times 10 to the 5 pascals, and the temperature of the gas is constant. So for this one, we want to use the correct equation from the physics equation sheet, and essentially we should be able to know that pressure multiplied by volume should give us a constant. And so we'll use K to represent that, but essentially that at different pressures and volumes, when you multiply them together, you should get the same number. So if we do 1.6 times 10 to the 5, multiply by 9 centimeters cubed, and we work that out, we should get 1.44 times 10 to the 6. And this 1.44 times 10 to the 6 is going to stay constant. So now when we have a pressure of 1.10 times 10 to the 5, multiply it by some unknown volume V, this should still equal 1.44 times 10 to the 6. And now it's just a simple case of rearranging the equation for V. So V would then equal 1.44 times 10 to the 6 divided by 1.8 times 10 to the 5. And when you plug that into your calculator, you should get a volume of 8.0 centimeters cubed. And that is given that is your answer there. 7.5, figure 14 shows a person using a bicycle pump to inflate a tire. The internal energy of the air increases as the tire is inflated. Explain why. Well, internal energy is all to do with the energy of the molecules themselves. And so when we start to pump it, we do work on the air. So we do work on the air when we pump the tire. And as a result, the temperature of the air increases. And so with internal energy, when you increase the temperature, that increases the internal energy of the molecules. And so when we do work on the air, that energy has to go somewhere, and that energy actually ends up increasing the temperature. So it's transferred as kinetic energy or thermal energy and then kinetic energy. Question 8 then. Nuclear power stations generate electricity through nuclear fission. Electricity can also be generated by burning shale gas. Shale gas is a type of natural gas that's trapped in rocks, and it can be extracted by a process called fracking. There's some evidence that fracking causes minor earthquakes. Burning shale gas adds carbon dioxide into the atmosphere. So our question is basically, we want to describe the advantages of nuclear power compared to using shale gas to generate electricity. Now, shale gas you might not be familiar with, but it's giving you all the information you need in this paragraph here. So the first advantage for nuclear power should jump out at you. There's no carbon dioxide emitted for nuclear power. And that means that basically it doesn't cause global warming. As a result, there's no global warming emissions. There's no greenhouse gases emitted when you have a nuclear power station, so that doesn't contribute to global warming. Next thing is nuclear power doesn't cause earthquakes. We've got evidence here it causes earthquakes, so you can also say there's no earthquakes, and that would give us another mark. And lastly, we can say that there's more energy released per kilo of fuel. So this is one that you might just be aware of. When we have nuclear fission, it releases a lot of energy, and so basically you release more energy. Essentially per kilo of fuel. And so these would kind of be more than enough for your 3 marks there. And basically you can even give, that would be 1 mark, that would be your 2nd mark, could be your 3rd mark. And this is kind of another point that you could add instead of the other 3, any one of the 3. What is the name of one fuel used in nuclear power stations? So we should know here, uranium is used a lot. You could also say plutonium. 8.3, describe the process of nuclear fission. So this is a 4 marker, so you want to go step by step. So first of all, with fission, what actually happens? Well, a neutron is essentially fired at a nucleus and is absorbed by this nucleus. And generally, it tends to be quite a large nucleus. So that's kind of your first point. So what happens after the initial absorption? Well, this nucleus then splits into 2. You split into 2 smaller nuclei, we can call them daughter nuclei. Okay, so that's kind of your second point here. Okay, what is the next step after this? And this, when you actually have this process where it splits into 2, it doesn't just split into 2 daughter nuclei, it also releases energy. So this is kind of the key part of nuclear fission. When you use it to make nuclear power, it releases this energy. So that's what we're interested in. And again, we're not complete. It splits into 2, releases energy, and it also is the key part. It also releases 2 or 3 neutrons. Now, why are the 2 or 3 neutrons important? Well, this can cause a chain reaction. Okay, so for your 4 marks, that should be plenty. Question 9 then, figure 15 shows a coffee machine. The coffee machine uses an electric current or electric element to heat the water. The coffee machine has a metal case. Why would it be dangerous for the live wire of the electric cable to touch the metal case? Well, metal is a really good conductor. So if you have a live wire touching that metal, it's going to conduct that electricity, and you're going to present a risk of electric shock, because anyone that touches the case could then potentially get shocked because there's electricity flowing through it. 9.2, the power output of the coffee machine is 2.53 kilowatts. The mains potential difference is 230 volts. Calculate the current in the coffee machine. So if the coffee machine was to take in all this 230 volts and it's got a power rating of 2.53, Well, power, we should know, is equal to the current multiplied by the voltage. And so we can just rearrange to get the current. So the current equals the power over the voltage, and that is equal to 2.53 kilowatts. You need to convert that to watts, so times by 10 to the 3, divided by the voltage itself, which was 230. And so if you plug that into a calculator, you should get a current of 11 amps. 9.3, the coffee machine heats water from 20 degrees Celsius to 90 degrees Celsius. The power output of the coffee machine is 2.53 kilowatts, like we just said, and the specific heat capacity of water is 4200 joules per kilogram degree Celsius. Calculate the mass of water that the coffee machine can heat in 14 seconds. Well, first of all, we want to work out the energy transferred by the coffee machine. We've got the power as 2.53 kilowatts, and we know that it was switched on for 14 seconds. So what was the total energy output? Well, energy is equal to power multiplied by time, and so this is just going to be equal to 2530 watts multiplied by 14 seconds, and that should give you 35,420 joules. Okay, that's the first step. We've worked out the total energy transferred by the kettle itself, or sorry, the coffee machine. Next thing, we want to actually relate this to the energy that's going to be transferred to our water. So we should know that the equation E is equal to mc delta T, or mc delta theta, where m is your mass, c is your specific heat capacity, and delta theta is a change in temperature. And if we look at our question, we pretty much got all of these now. So the energy was given to us, and that's 35,420 joules. That's equal to the mass. So the mass is what we're trying to work out. So we just leave that as m, multiplied by the specific heat capacity, which is given to us as 4200 joules per kilogram degree Celsius. And we know that the energy is in joules, so we just need to make sure the other measurements are going to be in kilograms and then degrees Celsius. So delta theta is a change in temperature. So it went from 20 degrees to 90 degrees Celsius. So the change in temperature was 70 degrees Celsius. So we just do it in red. And so now then we can basically rearrange for the mass. So m is going to be equal to 35,420 divided by 4200 multiplied by 70. And when you plug that all into your calculator, you should get a mass of 0.12, and it's going to be in kilograms. Perfect. Final question then, question 10, figure 16 shows a wind turbine. At a particular wind speed, a volume of 2.3 times 10 to the 4 meters cubed of air passes the blades each second. The density of air is 1.2 kilograms per meters cubed. Calculate the mass of air passing the blades per second. And so we need, for this question, we need to relate the density, the mass, and the volume. And so density is always going to be equal. Density rho is equal to the mass over the volume. And so this time we want to find the mass of air, so we can rearrange for m. So m is equal to rho, the density, multiplied by the volume. And so that we can just plug in our numbers now. So the density of is 1.2, and the volume was 2.3 times 10 to the 4. And you put that into a calculator, you should get 27,600 kilograms. Cool. The power output of the turbine is directly proportional to the kinetic energy of the air passing the blades each second. Describe the effect on the power output when the wind speed is halved. So there's going to be a couple of effects here. The first thing is, if the wind speed is halved, well, the kinetic energy is equal to a half multiplied by m multiplied by v squared. So if we half v, that means that our kinetic energy is actually going to not just be halved, it's going to be multiplied by a factor of a half squared. So it's going to be quartered, essentially. And the next thing we need to understand is that the kinetic energy, what happens to the actual mass of the air passing the turbine if the wind speed is halved? Well, if the wind speed is halved, that means that we'd get half as much wind, or half as much mass passing through the turbine as well. And so that means the total kinetic energy would be halved again. So here this time we've got half the mass. which would mean that actually, if you were to plug this into our equation now, the kinetic energy flowing through, the kinetic energy transferred to the blades each second is now going to be a half multiplied by half m, because the mass is halved, multiplied by half v squared. Half v squared, which is the same thing as writing a quarter v squared on its own like that. So remember, half v all squared is equal to that, quarter multiplied by v squared. So we can see here essentially, if we were to write this out, the kinetic energy will be equal to half multiplied by a quarter, so 1/8 multiplied by half mv squared. So that's kind of our standard kinetic energy equation. We've multiplied by 1/8, so we can see that actually the effect on the power output is going to be proportional to the effect on the total amount of energy, and so the kinetic energy would decrease by 8, so the power output would decrease also by a factor of 8. So that's what you want to write for your 3 marks. Right, 10.3 then. At a different wind speed, the wind turbine has a power output of 388 kilowatts. The mass of air passing the wind turbine each second is 13,800 kilograms. Calculate the speed of the air passing the blades each second. Assume that the process is 100% efficient. Okay, so for this one, first of all, we take the power output being 388,000 watts. So you want to convert that straight away. And this is basically equal to the kinetic energy that is transferred, right? Because we've assumed this process is 100% efficient, that means that all of the kinetic energy was transferred to the power output of the wind turbine itself. So we can equate this to half mv squared, where this is the kinetic energy of the wind, or the air passing through it. And so then we can actually work out v squared here. So v squared is going to be equal to 388,000 divided by a half multiplied by the mass, and the mass is given to us as 13,800 kilograms per second, and so we can just plug that in. So half multiplied by 30,800, and so the reason why we can just plug that in is because the power output was 388 kilowatts. So this energy that we've equated here, this is basically the energy per second, right? So in 1 second, we said we had 388,000 equal to a half mv squared, and we used therefore the mass in 1 second as well, which was 13,800. So because everything is per second, we can use it as the energy, not just the power. And so if you plug this into your calculator, then essentially you should get v squared equals 56.2 meters per second, and therefore v would just be equal to the square root of that, and you should get approximately 7.5 meters per second. Okay, so hopefully that makes sense. That is all the questions for this paper, and yeah, we'll be back with part 2 hopefully soon. If you enjoyed the video, please subscribe and like.